All right, so different common problems in analytical chemistry. Oftentimes problems, especially initial problems, are qualitative in nature. We just want to know, is there lead? Is there too much carbon, or is there carbon dioxide in the sample? Is there gasoline in the water? That sort of thing. All right. Now, after we find that out, then we often will try to continue to develop methods that will give us quantitative information, right? But other times we'll be trying to look into the characterization of an analysis or characterization of a sample, or called characterization analysis. For example, we might want to know the chemical structure of a compound. All right, so the presence of a chemical is one thing, but identifying the chemical structure of a compound is also something that's important, and applying analytical methods to analytical approaches to identifying chemical structures is important. An equilibrium constant. Do you remember what an equilibrium constant is? I'm not sure. So let's talk a little bit about an equilibrium constant, right? So in an equilibrium constant, what we're saying is that there is a process. Now, generally in chemistry, Chem 105, Gen Chem, we will say things like A reacts with B to form C, and this is in equilibrium. And it could be, more than one chemical sort of thing. But sometimes, and then the way that we express how this equilibrium is situated at when it reaches equilibrium is a equilibrium constant, right? So the equilibrium constant equals the concentration of C raised to its exponent, all right? So if we have exponent x there, times the concentration of D, which is the other product, raised to its exponent, let's have y there as its exponent, over the concentration of A raised to its exponent times the concentration of B raised to its exponents. So these are, or this statement here, at equilibrium is what our equilibrium constant is. Okay? Now, sometimes it's a chemical reaction, but sometimes it's just a complexation. So for example, if I have iron, iron, and this iron is complexing with a chemical called EDTA. Have you ever heard of EDTA?
No, I haven't.
Okay, so let me show you what EDTA looks like. All right, so here is an iron EDTA complex. You have the orange iron there, and these black molecule or atoms here are carbon, the white ones are hydrogen, and the red ones are oxygen. And if I bring up this one here, you can see it differently as well. The oxygens here are providing electron density to complex the iron, along with the lone pairs on the nitrogen here are all donating electrons, and we got 1, 2, 3, 4, 5, 6 directions in which electron density is being donated to this iron, and each one of these forms a little bit of a complexing bond, and although they can release one at a time individually, the likelihood of all 6 of them releasing at the same time is minimal. And so what happens is the iron binds to this EDTA. We don't really get a significant chemical change, but the iron is complex there, we say, and it can come out, but the concentration, so then we use an equilibrium statement to express what's going on here. Iron combining with EDTA to form an iron EDTA complex, EDTA complex, right? There is an equilibrium, but the K value here is, and the number suggests that most, if not almost all, of the iron is bound to the EDTA. What would the K number be if at equilibrium almost all of the complex was like this and not like this? Would the K value be very large or very small?
What would the K value be if it was all iron EDTA and not separate?
Yeah, what would the K value be here if it was almost all this and not separate? Would it be a very large value or a very small value?
I'm not sure.
Well, see, remember that K is the products over the reactants. You see that?
Okay.
So if the concentration here, 0.1, 0.03, whatever number you want to put in there, right? The concentration of the iron EDTA complex over the concentration of these. Now these are going to be very, very low because we said that almost all of it is over here. So over a very small number, right? So iron, and the EDTA by itself without the complexation, right? Large number, or a relatively large number, not huge, but I mean much larger than these numbers, divided by these very small numbers is going to result in a very large value. So a large K, or a large equilibrium constant, means we have more product. So if this is a large value, that means more product at equilibrium. Now, what do you think? If this is a very large value, does that mean this reaction never goes back?
I don't know.
Well, the reaction is always going back and always going forward, but with a very large value, the rate at which it goes back is very slow compared to the rate that's going forward. If you have this sort of a setting, though, and you input an element, a metal that will bind even tighter to EDTA, then what will happen is gradually that metal will bind to EDTA and the iron will be left out, right? Because it is turning over little by little in terms of going back to the dissociated form, right?
Okay.
So that's our example of an equilibrium constant. Particle size, that's pretty self-explanatory. So in this section here, it talks about a couple of modern methods for quantitative analysis or qualitative analysis called infrared spectroscopy or nuclear magnetic spectroscopy or mass spectrometry, all of which are really important techniques to understand. However, it's kind of assuming in this book or this analytical text here that these techniques have been provided for you previously, specifically probably in an organic chemistry class. I'd like you to email me and let me know if you are familiar with these techniques or if you are not. Okay. In fact, instead of emailing it to me, what I'd like you to do is make a video telling me what you know about infrared spectroscopy, nuclear magnetic resonance spectroscopy, and mass spectroscopy. Okay. And from that, we'll know where we're at and where we have to go. Okay. So an assignment, make a video telling me about your familiarity with these techniques, these instrumental techniques. Another type of analysis, which we call fundamental analysis, or just receiving a general understanding of what is occurring. This type of thing, this type of analysis doesn't necessarily lend itself initially or isn't driven initially by the need to make a new analytical method, but it's incredibly powerful. Having a fundamental understanding of anything around you can change your understanding and the interpretation, our abilities drastically. So that's one of the things that really drew me and draws others to chemistry is if you understand what's going on, then you're almost unlimited in your ability to improve whether it be an analysis, any system. You can give quality, value to a company, even if they're not even a chemical company. Understanding the fundamental process of what's going on. And a lot of terms in business kind of lend this idea. I mean, they talk about root cause analysis, meaning identifying the real issue that's causing the problem. All right, so fundamental analysis, very important. Okay, good. So that finishes us. Well, I guess we could go and look into some of these problems a little bit. So for each of the following problems, indicate whether its solution requires a qualitative analysis, a quantitative analysis, a characterization analysis, and or a fundamental analysis. More than one type of analysis may be appropriate for some problems. All right, the residents in the neighborhood near a hazardous waste disposal site are concerned that it is leaking contaminants into their groundwater. What do you think?
Well, I guess you just want to know, right? If there's something bad in the water, you want to know.
All right. So if it's leaking something like, let's say, hot water into the surroundings, is that a problem?
Well, I guess that's not a problem, but yeah, so you want to know if it's hot water or something like gasoline.
Okay. So in that perspective, you could say it's kind of a qualitative problem, maybe. But did you know that if you release too much hot water, you know what happens if you release too much hot water into a stream?
Into a stream?
Yeah.
Like a river?
Yeah.
It makes it warm?
Yeah, and then what?
Does that kill the animals?
It does, but it can't. Now, do you know why?
No, I'm not sure.
Because as you increase the temperature of water, you change the solubility of gas in it, right? You change the solubility of gas, and it actually decreases the solubility of gas. Therefore, fish will die if water gets too warm, because all of the oxygen most of the oxygen will leave the water, decreasing the amount of oxygen available. That's one reason why you want to be careful about putting a fish tank near a warming source, right? Okay. In terms of a characterization analysis, could you see any way that might be important?
Well, if they're leaking anything, it could be a problem.
It could be, but understanding what it is that they're leaking might be important. So if you do have a chemical, then trying to characterize that chemical, find its chemical structure, might be important, right?
Okay, yeah.
All right. I'll let you kind of go through the rest of those and become familiar with those. All right. Those are some good possible types of learning questions for quiz questions later on, right? Here's a nice article. When Machine Tastes Coffee, Instrumental Approach to Predict the Sensory Profile of Espresso Coffee. All right. Let's read that. That's up on the Canvas site. Let's read that and then read through the rest of this here. I'll let you guys do that on your own. And focus on the results of the model by examining the visualization in figure 3 and 4 of the paper. All right. There's some other specifics in here. I'll let you read through this and learn more about what they're describing here, what we're trying to learn from this article. All right, so why don't you go ahead and make that video that we were talking about, and also finish up talking about these B through F for us in terms of quantitative, qualitative, characterization, and then also let's read this article and answer these questions and kind of discuss what we're learning from the reading. Okay, good.